Classroom Idaho, Learning at Home. The Idaho State Department of Education and Idaho Business for Education is partnering with Idaho Public Television's education team.
Hello again, sixth graders, and welcome back to Classroom Idaho. My name is Mrs. Young, and I'm a sixth grade teacher at Kuna Middle School in Kuna, Idaho. Today, we are going to continue talking about physics, and we're going to talk also about Newton's second law. As you might remember, physics is the study of motion, energy, and forces. And a lot about what we know about these things is all thanks to this guy, Sir Isaac Newton. We can thank him for discovering that gravity is a constant, and he also created Newton's laws. He has 3 laws. And the amazing thing is that even though he lived a really long time ago, from 1643 to 1727, we still use and apply Newton's laws today. It's pretty amazing. All right, so as we continue our discussion about Newton's laws, we really need to go back and review the concept of force. Okay, wait. No. I'm not talking about the force. The force about, that multi-billion-dollar movie franchise. We're not talking about the force. We're not talking about that force. We are talking about this force, the push or pull on an object. Now, remember last week, we talked about Newton's first law quite a bit. And what we learned is that Newton's first law says an object at rest will stay at rest, and an object in motion will stay in motion, unless an outside force acts upon it. So basically, what that means is that things like to keep doing what they're already doing. And it doesn't matter what you say, you can try to convince things. Nothing's gonna move until you apply force, because it takes force to change the motion of an object. So in order to move things, not only do we have to have force, but we actually have to have unbalanced forces. So let's go back to our force diagrams that we talked about last week. So here's a basic force diagram. Let me just walk you through this again. So here we have a basic picture, and it's supposed to represent a table and a physics book. And this is called either a force diagram or a free body diagram. And we have arrows here that are representing the forces that are in play. So what we need to know about the arrows is that the size of the arrow matters, and the bigger the arrow, the larger the force. And also the arrow is indicating the direction of the force. So if we break this down this way, we can see the arrow pointing downward. Gravity is pulling down on the book. And then we also see an arrow going upward, and this is indicating that the table is pushing upward on the book. So we have balanced forces. You can see those arrows are even without a number. We know that those forces are balanced. That book is not going to move. So let's look at another example. So here we actually have some numbers represented as well. And you may notice right away that it's exactly what we said with arrows, size matters. So if we look, we have 2 arrows that are pointing down, representing that gravity is pulling downward. And you can see that there are numbers next to them. And it's very clear the larger number is next to 130 versus a smaller arrow, which is next to the number 50. So definitely the size is relative to the number. So And here, because there's two, there's indicating two, we would do the math. 50 plus 130 is 180. And if you notice that uppercase N there, that is the indication of newtons, which is the unit of measurement that we use for force. So thanks to our friend Isaac Newton. So anyway, back to the diagram. So we can see here that the force is pushing up on the shelf, or the shelf pushing upward. You can see there's 100 newtons and 80 newtons. And again, we can see that the arrows are definitely relative to the size of the force. But again, those arrows are going in the same direction, so we're going to add those two together. So the gravity pulling downward is equal to 180, and the force on the shelf going upward is 180 as well. 180 is equal to 180, so our forces are balanced, and our base isn't going to fall off of the shelf. Let's go on to one that shows some unbalanced forces here. So this is a picture of a helicopter, and again, you can see that the size of the arrow really does make a difference. So when we have 200 newtons, and that is gravity pulling downward on the helicopter, versus 70 newtons of the helicopter pushing up again, or pulling up against gravity, so that's measured 70 newtons. So clearly this helicopter is just simply coming in for a landing. Okay, so why don't I give you another example, maybe a little more close to real life. Okay, so here's another example of balanced versus unbalanced forces. Just a simple game of tug of war. We know when we play this game, it's a lot more fun if the teams are even. If you have all of the stronger people on one side, it's not going to work. It's not going to be a contest at all. It's far more challenging and fun when the teams are equally set up. But we know what happens. People start to get tired, maybe people lose interest, or people gain interest and jump in. And then when the forces become unbalanced, or the teams become unbalanced, then we can end up with a little bit of a mess. Okay, so we really can't talk about Newton's first law without first talking, we also need to talk about inertia. And this is, of course, the idea that objects are going to resist changes in motion. And the example of playing a video game with your friend, you are really excited, that's where you want to stay. You do not want to move. When your mom calls you to do the dishes, you are going to resist that change. You don't want to do it. It's really the same thing. Okay. So now what I'm going to do is I'm going to show you on one of the inertia videos that I made last week, just a short little one, just to remind you about what we're talking about, objects resisting change in motion. Well, now we have a different way to illustrate inertia, and this one is one of my favorites. Kind of a crazy way to dye Easter eggs, but it's lots of fun. So if you remember, an object in motion stays in motion, an object at rest stays at rest, unless an outside force acts upon it. So we're going to test this now. What we see here is we have our egg dye down at the bottom, and we have our pie tin here, and our egg on top with a toilet paper roll. Now, theoretically, what should happen is I am going to apply force only to the pie tin. And because I'm only applying force to the pie tin, the egg shouldn't go in the same direction as the pie tin. Instead, the egg should stay and then be directly pulled down by gravity. Now, let's see how it works. Are you ready? We're going to start. Here we go. This could be great, or it could be a big mess. All right. 1, 2, 3. Yes! Inertia! Okay, So, and here's another example, and this is why the concept of inertia is so important. So, inertia in U. So what does this really mean? Why is this important to me? So, say for example, you're driving down the street in this really cool car, and you're going about 50 miles an hour. Well, you are going 50 miles an hour in the car. You are going 50 miles an hour. The car is going 50 miles an hour. But if something happens where there's something where you have to stop, a brick wall, for example, or probably more likely, maybe a stoplight or somebody running out into the street. Anyway, you're going 50 miles an hour in the car. When you apply the brakes to the car, what is going to happen is that is only going to stop the car. That's not going to stop you. And unless you wear something like your seatbelt, then you're going to have a big problem. Okay, so that is why we often call Newton's first law the seatbelt law. Okay, so an object in motion stays in motion, an object at rest stays at rest. So why is it that things on Earth don't move or stay in motion forever like they do in space? There's no friction and there's no gravity in space, so things could conceivably move on and on and on and on and on in space. However, why don't they do that on Earth? I mean, we know that when we throw a ball up into the air, it's eventually going to come down, and because of the force of gravity. And when it does hit the ground, it's going to roll gently to a stop because of friction. So, an object in motion stays in motion, and an object at rest stays at rest. And Newton's second law really continues on from there, and it describes what happens if some net force is present. So, and this law is really talking about the formula force equals mass times acceleration. And really, we can use this equation to do calculations about force, mass, and acceleration. And because don't forget, Newton really was a mathematician, and this is where we talk about how we're measuring forces, but we're also able to predict forces. Newton did the math behind what's really happening. So, okay, sixth graders, so what we're going to do now is we're going to have a little twist on that magician trick that we just did. That one, it was very clear. Inertia was definitely at play, but if you notice, both of the objects were kind of the same. One of the things that you need to know about inertia is that mass matters. How much mass an object has really makes a difference as to how much gravitational pull is on an object. And we know when there's a lot of gravitational pull, there's more resistance to the change in motion. So we're going to give this a try, and this time we are going to try 3 very different objects. They all look the same, but their mass is different. For example, this one here, this is an empty water bottle. There's nothing there. It can fall over pretty easily. Next, we have a water bottle that's about halfway full. It's a little heavier, definitely a little sturdier. And then we have this one. This one is full to the top. All right, so what we are going to do is we're going to try the magician trick again. But what I want you to do is I want you to predict what you think is going to happen. Which one of these is going to be left standing? All right, and here we go. And 1, 2, 3. Okay, was your prediction correct? Interesting. Again, mass matters. Okay, so really, honestly, the heavier objects require more force and lighter objects require less force. So let's look at it again this way. So you're driving down the street in a car, and you come to a stoplight and there happens to be a truck sitting next to you. Now, conceivably, let's think about you applying force when the light turns green. You apply force to the accelerator just like the truck driver does. But your car is going to accelerate a lot faster than the truck will because the truck has more mass. And that is what we're going to talk about a lot, is about how mass affects acceleration. Okay, so here's another example. Or we can look at it this way too. So have you ever played soccer? Well, what about kicking a soccer ball? Instead of kicking a soccer ball, you kick a bowling ball instead. It would hurt your foot, right? But it would also take a lot more force to move it. So really what is happening is the foot is applying force, that push or pull, and it's causing it to accelerate, which, by the way, is acceleration is the measurement of an object's changing speed. So back to the example. So what if you tried to kick a bowling ball with the same amount of force? Would it accelerate the same? No, it's not going to. Let's kind of try to work out the math on this, okay? So remember, Newton was a mathematician, so this is all about the formula of force being equal to mass times acceleration. So let's look at this in regards to the soccer ball. So a regular soccer ball has a mass of 0.45 kilograms. And if you want to accelerate that ball at the rate of 8 meters per second squared, how much force would you need to apply when you kick the ball? So let's work through the formula. So basically, when we're looking at this, we plug the numbers into the formula. So we know that we have where force is equal to mass times acceleration. So our mass is 0.45 kilograms times 8 meters per second squared, and that is equal to 3.6 newtons. Now remember, newtons with an uppercase N because of our friend Isaac Newton. Okay, so why don't we go ahead and look at a demonstration, and let's see what happens when we apply the same force to objects with two different masses.
All right, so we have spent a little time talking about Newton's second law and the formula and the math behind it. So now what we're going to do is we're going to bring that math to life with an actual demonstration, a physical demonstration. So if you want to try this at home, it is a lot of fun. A couple things that you'll need a ruler, some sort of measuring device, a meter stick or a tape measure. You're going to need some tape if you're going to be marking things off, or a marker, depending on where you're marking things off. And then the key to this demonstration is that you need to have two balls that are approximately the same size but different mass. I chose a ping pong ball and a golf ball. Most people have at least one or the other, but anyway, you can use anything. So we're going to go ahead and set up this demonstration, and we'll see you in a sec. All right, so now we are going to change the variable a little bit. The last one, we changed the variable of mass. And now what we are going to do is we are going to change the variable. Instead of mass, we are going to keep the mass the same and the force. We're going to change the force to see if that makes a difference. Because remember, it's dependent upon mass and force. All right, so here we go. I've got my little scale here so I know how far to pull back my ruler. So we're going to start with 5 centimeters like we did before. And 3, 2, 1. Go. All right, 80 centimeters approximately. And now we're going to try this again. But now I'm going to double my force. I'm going to pull this ruler back. It's pretty bendy. I'm going to pull this back, and then we are going to see if It truly does make a difference. All right, here we go. In 3, 2, 1. Whoa, big difference. All right, I think that was pretty clear.
And now let's go ahead and see what happens when we apply more force to an object with the same mass.
Okay, so we are all set up and ready to conduct this demonstration. So what I have here is I have my scale here that is going to help me really keep track of how much force I'm using to hit my golf ball and my ping pong ball. And then I just have my ruler. So, and I like to use like a little penny or something like that that just kind of lifts the ruler off the table just a tiny bit. So we're going to start with the ping pong ball first. I'm going to pull this back to 5 centimeters and then I'm going to let it go in 3, 2, 1. Okay, that just went flying. Pretty easy to determine that that was a successful run. We're going to try the same thing. The key is that I am using the same amount of force. The thing that is different this time is that this has significantly more mass. And let's see if we can see a difference in the acceleration. All right, here we go. 3, 2, 1, go. Interesting. Same force, different mass.
All right, so what we discovered is that force is directly proportional to mass and acceleration. So increasing the mass of an object is going to decrease acceleration if the same force is applied. But if you increase the force, it will increase its acceleration if the mass stays constant. And that's exactly what we did in that video. So in comparing two objects with different masses, it's very clear that when the same amount of force is applied, the acceleration of the ping pong ball is much greater due to the lighter mass. So, and then increasing the amount of force clearly resulted in increased acceleration. So if you want to maybe think about relating this to maybe baseball or different cars of different masses, all that kind of stuff works the same. All right, so last example. So basically what we're talking about is that the force of an object comes from both mass and its acceleration. So think about a glacier, for example. It really has a very high mass, but it can still have a great force even though it's changing speed very slowly because it's all directly proportionate. And conversely, when we shoot an arrow, a small mass, which is really a smaller mass, it's going to change speed very quickly, which is going to give that high acceleration, and it's still going to have that high rate force. Okay, guys, that's it. That is all the time that we have today, and I appreciate that you were staying with me as we really explored more about force and how force is directly proportional to mass and acceleration. I hope that bringing that math problem to life for you really helped you understand about how force of an object comes from both more mass and its acceleration. Thank you so much for watching this week. I appreciate you and I hope that you're doing well, and I can't wait to see you again. Have a great day and we'll see you next time.
Funding for Classroom Idaho has been provided by the Friends of Idaho Public Television, the Idaho Public Television Endowment, and the Corporation for Public Broadcasting.
You're watching Idaho Public Television's Create channel.